नमस्कार दोस्तों, वेलकम टू गेट वाला। मैं हूं सतीश कुमार द्विशेट्टी, फैकल्टी ऑफ इंस्ट्रूमेंटेशन। मैं आप सब लोग को यहाँ स्वागत कर रहा हूं यूट्यूब चैनल पर। बहुत सारे लोग वेट कर रहे हैं मेरे सब्जेक्ट के लिए, ऑप्टिकल इंस्ट्रूमेंटेशन। लास्ट 3 सेशंस में हमने सेंसर्स एंड इंडस्ट्रियल इंस्ट्रूमेंटेशन डिस्कस किया था। आज हमने ऑप्टिकल इंस्ट्रूमेंटेशन डिस्कस कर रहे हैं। सो जितने लोग लाइव में हैं मुझे एक बार वॉइस कंफर्मेशन कर दीजिए, ऑडियो वीडियो सब कुछ क्लियर या नहीं। सो ऑप्टिकल इंस्ट्रूमेंट्स के लिए क्या करने हैं। सो ऑप्टिकल इंस्ट्रूमेंटेशन में पहले टॉपिक है ऑप्टिकल सोर्सेस। पहले टॉपिक है ऑप्टिकल सोर्सेस। सो ऑप्टिकल सोर्सेस 1, इसके बारे में हम डिस्कस करेंगे। सो क्या क्या होगा इसमें। सो ये फर्स्ट लेक्चर है। सो फर्स्ट ऑफ ऑल, इफ यू सी द सिलेबस, if you see the syllabus overview of the optical instrumentation, the complete syllabus of optical instrumentation is categorized like this. So this is a syllabus overview. So the syllabus overview is like this. Okay, so if you see the syllabus, the optical sources, this is optical sources like LED, laser, etc. Next, optical detectors like LDR, photodiode, etc. This etc is very important. Why? Because in this etc there are so many things will come. Next comes the basics of optical fibers. Basics of optical fiber. Next, after this, basics of interferometry. Basics of interferometry. And in addition to this, we have UV visible IR spectrophotometers. Next comes the mass spectrometer. Mass spectrometer. Okay, so please make a note of this. ऑडियो वीडियो सब कुछ क्लियर है, मुझे एक बार कंफर्मेशन कर दीजिए। ये है कंप्लीट सिलेबस। सो आई विल ट्राई टू ब्रीफ आउट द सिलेबस हियर। So optical sources like LED, laser, etc. Optical detectors like LDR, photodiode, etc. Basics of optical fiber, basics of interferometry, UV visible IR spectrophotometers and mass spectrometers. Okay, so now first we'll start with the UV sources. So these are the examples for the UV sources. Ultraviolet source. So generally when the ultraviolet light is going to be generated, when electron touches the gaseous molecule, that gaseous molecule outer orbit electron will be released. So 2 electrons will be coming out. Okay, so this is the nucleus. Around the nucleus we're having the orbits like this. Okay, so these are the electrons roaming in the outer orbits. So this is a nucleus. So when outer side electron is coming and hitting, then these electrons are going to come out. The hitting electron and the triggering electron both are going to come out. So the outer orbit electron and the hitting electron both are going to be come out. So 2 electrons are going to come out like this. So this is electron 1 and this is electron 2. So this is the electron 1, which is outer orbit electron. This is electron 2, which is coming from the outside. When it hits, 2 electrons are going to come out. Okay, so these 2 electrons, actually ये electron है ना, this electron was roaming in this orbit. So when this electron was roaming in this orbit, it is having the kinetic energy. So that kinetic energy is released in the form of light. So that light is called UV light. So we are having the UV light, ultraviolet discharge light. So which is what we call as UV light. UV light. Okay, so that's how the light is going to be generated. Anybody is there in the live? Okay. So the UV sources. So there is a UV sources. There are different types of UV sources. So one is a hydrogen lamp. One is a hydrogen lamp. Other one is a deuterium lamp, mercury lamp, UV detectors. Detectors are different. UV source is different. Detectors are different. So what a detector will do? So the detector will do like this. The detector will convert UV radiation into current. So UV into current. Okay. So these are iphotons. So these are UV detectors. So the examples for the UV detectors are photoemissive cells. So they will work on the concept of photoelectric effect or photoemission effect. Photoelectric effect or photoemissive effect. फोटो इलेक्ट्रिक इफेक्ट और फोटो एमिसिव। जितने लोग लाइव में हैं मुझे कंफर्मेशन कर दीजिए एक बार। Nobody is watching. Okay. So this is the UV sources. Next comes the visible sources. So visible radiation, all of you know it. So visible radiation is VGR, violet, indigo, blue, green, yellow, orange, red. So the elements are tungsten bulb, next tube light, sunlight, because sunlight contains, actually sunlight contains, so these are sunlight. So it contains visible, IR and UV. So this is 380 nanometers to 780 nanometers. Violet, indigo, blue, green, yellow, orange, red. Okay, so please make a note of these all points. Violet, indigo, blue, green, yellow, orange, red. Okay, so tungsten filament bulb, tube light, sunlight. But sunlight contains what you know? Sunlight contains near UV to near IR. So this is the near gene. So this is what we call as, so this is a UV radiation. So this is a near UV. This is a far UV. So this is a near IR. This is a far IR. So it contains from center of the UV to the center of the IR. So this particular zone, mid UV to mid IR, mid UV to mid IR. It does not contain far UV and far IR. Okay, so it contains this part, this complete 100% visible, and this part. So please make a note. So sunlight contains 275 nanometers to 2750 nanometers. That is the lambda of the sunlight. Please make a note of these points. Okay, all of you are getting my point? Yeah. If you have any doubts, let me know, my dear. Next comes the candle light. Next comes the LED laser. Okay, especially laser la, helium neon laser, not all lasers, helium neon laser only. Helium neon laser only. Helium neon laser only. Okay, yeah, chalo. Now let us go for, first we'll talk about LED. LED is a light, this is optical source which comes under the category of visible radiation, light emitting diode. Okay, so it is different from the UV light. UV light will be invisible, but whereas LED is visible. Okay, so LED comes under forward bias. So LED is a forward bias. So the materials used for LED are gallium arsenic, gallium phosphide, gallium indium arsenic, gallium sulfide. So these all are the semiconductors materials. What materials? These are all semiconductors materials. So this is a valence band, this is a valence band, this is a conduction band. So electrons are moving from the ground state to the higher energy state. So this is a E1, this is a E2. So the energy gap is equal to E2 minus E1. Energy gap is equal to E2 minus E1. So when you give some input bias current, so LED works in a forward bias. So this is a LED diagram. So when you give a forward bias like this, when you give a forward bias like this, is the forward bias. So we are giving the bias current. So because of the bias current, so there is a glow. There is a glow. Okay, so that's how it moves. So input we are giving the bias. So when you give the bias, these electrons are jumping from valence band to conduction band. So they're jumping from E1 to E2. So once they move to the higher energy level, again they cannot sustain over there for longer moment of time. So this is the E1 valence band. So this is the E2, this is the conduction band. Electrons are moving from the lower energy level to higher energy level. So at the higher energy level, the time is 10 to the power minus 8 seconds. So more than that time they cannot sustain. So once the time is over, the electrons are going to fall down. So when the electrons are falling down, then what happens? The photons are going to be released. So these are the photons. These are the photons. Energy gap is greater than hc by lambda. So this is the energy of the photon. This is hc by lambda. Okay. So lambda is the color. H is the Planck's constant. So this H is given as some values. So what are the values of H? This H is given as 6.625 into 10 to the power minus 34 joule second, and this is 6.625 into 10 to the power minus 27 ergs second. Okay. Next, 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. So 1 by 1.6 into 10 to the power minus 19 electron volt is equal to 1 joule. So if you substitute that, I'm going to get 4.145 into 10 to the power minus 15 electron volt second. So that is the H. Okay, so please have a note of this. Electrons are jumping from valence band. Okay, note down. चलो. So 4.145 into 10 power minus 15 electron volt second हो गया. चलो next let us see characteristics of LED light. So the LED light characteristics are like this. So as I mentioned, energy of the photon is equal to hc by lambda. So energy of the photon is equal to hc by lambda. So this is the lambda. Okay, energy of the photon is equal to energy gap. So these are the photons. But the photons are dispersive in nature. They are not in phase. The photons which are released in the LED, they are quite different from the laser light. लेजर में जो कांति आ रहा है ना वो इन फेज रहता है, वो कोहेरेंट रहता है, फोकसिंग रहता है, हाईली डायरेक्शनल रहता है. लेकिन एलईडी में जो लाइट आ रहा है, सो दैट लाइट इज कंप्लीटली डिस्पर्सिव लाइट. सो इफ यू सी द कैरेक्टरिस्टिक्स ऑफ एलईडी लाइट, इलेक्ट्रॉन होल पेयर रिकॉम्बिनेशन. So this electron hole pair recombination, so they will go up and they will fall down. So they're going to be fall down like single step transfer. So this particular recombination is called as radiative recombination. So radiative recombination bolte hai. So there are different properties. They're having different phases. So they're not coherent. So isko bolte hai incoherent bolte hai. Next, they're having different directions. So they're called as dispersive light bolte hai. Next, different lambdas. So they're called non-monochromatic bhi bol sakte hai. They're not monochromatic. They're not focusing. They're not coherent. So these are the properties of light. So incoherent, dispersive, and non-monochromatic is the feature. Okay, so let us go for the next one. So this one, if you see, silicon diode. So the same to same, if you see the silicon diode is different from the LED diode. So that LED is also made by PN junction, and this silicon diode also made by that is also forward bias, this is also forward bias. But in LED we observe the light, whereas in PN junction diode we observe the heat. So if you see, this is a valence band, this is a conduction band, so energy band E1. In addition to this lower energy, higher energy, there exists a metastable state. So this is a metastable state. So this metastable state is, this is E2. So this is E1, this is E2, this is E3. Okay, so the electrons which are staying in the higher energy level, they will stay up to 10 to the power minus 8 seconds. That is common. But this time they cannot jump directly to the ground. So they will go to the intermediate state like this. They will go to the intermediate state like this. They will go to the intermediate state like this. So this is what we call as metastable state. So this is 10 to the power of minus 5 seconds. 10 to the power of minus 5 seconds they will wait. So after the 10 to the power of minus 5 seconds, the electrons will be falling down. They will exist there up to 10 to the power of minus 5 seconds. And after the 10 to the power of minus 5 seconds, they will come down. So in this process, the energy is related part by part. The energy is released part by part. So that is what we call as heat. That is what we call as heat. Okay. So it is not emitted in the form of light, but is emitted in the form of heat. So this heat is called, the recombination which generates the heat is called as non-radiative recombination. What we call this as non-radiative recombination. Non-radiative recombination. Now let us see here. So this is the scenario of the diode. Metastable state. So why? Because the lifetime comparatively here the lifetime is more, 10 to the power minus 5 seconds. So when the lifetime is more, there the electrons will sustain for a good amount of time. Okay, 10 to the power minus 5 seconds. So that particular state is called as metastable state. That particular state is called as metastable state. Okay, so now what I understood. Now these are the fundamental differences between the LED and the PN junction diode. If you see the LED diode and PN junction diode, so LED materials, these are the materials: gallium arsenic, gallium phosphide, gallium sulfide, gallium indium arsenic. Whereas PN junction diode materials, germanium, silicon, and selenium. Okay, chalo. Now these are the direct band gap materials. So these are the direct band gap materials. So these are the indirect band gap materials. Direct band gap materials, indirect band gap materials. So this is the forward bias, this is also forward bias. Okay, so this emits a light, so light emission is more, and here heat emission is more. Heat emission is more. So probability of light is more than the probability of heat. Your probability of heat is more than the probability of light. सिंगल स्टेप ट्रांसफर बोल सकते हैं इसको, इसको टू स्टेप ट्रांसफर बोल सकते हैं. So please make a note of all these quite differences. When you're writing the non-gate exams also, this will be very, very important. Chalo. Now let us go for one of the important thing. So see this. Now if you see this, what happens here? What happens here? These particular electrons are falling down. In LED, what happens? Very literally, the photons are going to come like this. Okay, and heat is going to be generated here. Heat is going to be generated here. Okay, so the time interval between the two successive radiated recombinations, we can call it as TRR. So what we call this as TRR. Time interval between the two successive radiated recombinations are called TRR. Next, TNRR. Time interval between the two successive non-radiated recombinations. So that means one photon has fallen down. At that time, one electron has fallen down, light has been released. Next electron has fallen down, another light has been released. Next electron has fallen, another light has been released. So that means the time interval between the two photons is very, very less. Okay, TNRR, time interval between two successive non-radiated recombinations. Okay, so next comes 1 by TRR. So this 1 by TRR is called RRR, rate of radiative recombination. What we call this as rate of radiative recombination. Next, 1 by TNRR. So this is 1 by TNRR. So what is this called as 1 by TNRR? So that is called RNRR. So rate of non-radiative recombination. Rate of non-radiative recombination. So for LED, time interval between the two successive radiative recombinations is lesser than time interval non-recombination. So rate of radiative recombination is more than the rate of non-radiative. So for LED is different. For PN junction diode it is different. For PN junction diode, time interval between the two successive non-radiative recombinations is lesser than time interval in rate of radiation. So rate of non-radiative recombination is faster or higher than the rate of radiative recombination. Okay. Chalo, note down. One of the important points. Please note down this. Now let us go for this efficiency. TRR is less than TNRR. RR is equal to rate this. Total rate is RRR plus RNRR. So this can be taken as 1 by TRR plus 1 by TNRR. So R total will come like this. So quantum efficiency of LED can be taken as internal quantum efficiency. So this is one of the expected question here. So internal quantum efficiency, what we call this as internal quantum efficiency. Internal quantum efficiency is given as rate of radial recombination over the rate of total recombination. Rate of radiation recombination over the rate of total recombination. Make a note of these points. Rate of radial recombination to the total rate of recombination. Internal quantum efficiency. Okay. So now this is the bias current. That bias current goes, and this is a gallium arsenic. Okay. So now the light is going to be generated here. LEDs are coming. Light is going to be generated, but bahar se light aayega. So this is internal quantum efficiency. Optical power internally generated, not even here actually. So this is the internal. Okay. Chalo. Next comes external quantum efficiency. So this is internal, this is external, so this is coupling efficiency. Okay. Chalo. So if you are taking LED, for LED number of EHPs are injected and number of photons are coming. There is another way of representing the quantum efficiency. So there are certain EHPs are injected, as a result we are getting the photons. So internal quantum efficiency defined as number of photons generated by number of EHPs injected. So this is another formula. Number of photons generated by number of photons injected, this is another formula. So when you multiply with 100, so we are going to get the internal quantum efficiency. So when you are multiplying with 100, we are getting the internal quantum efficiency. Internal quantum efficiency. So please make a note of these points. Now let us go for one derivation. So internal quantum efficiency is given as number of photons generated per time and number of EHPs injected per time. So number of photons generated per time is called the rate of photons. Number of EHPs injected is called rate of EHP. So rate of photons is optical power by energy of the photons. So units are per second. Rate of EHP is bias current by Q, that is also per second. Okay. So internal quantum efficiency is given by rate of photons by rate of EHP. So P optical by energy of the photon divided by I bias by Q, that will give us P optical by energy of the photon Q by I bias. So if you see, this is the actual formula, but this P optical by I bias can be called as responsivity. Okay, so this P optical by I bias is called the responsivity. So responsivity is defined as optical power generated by the bias current supplied. Optical power generated by bias current supplied. So two important formulas for the LED chapter for the gate examination. जितने लोग लाइव में देख रहे हैं, मुझे थम्स अप दिखाना है. जितने लोग लाइव में है, कुछ ना कुछ रिस्पॉन्स देना है. मिनिमम कर्टसी है ये, क्योंकि ये ऑप्टिकल और इंस्ट्रूमेंटेशन क्लासेस यूट्यूब में प्लान नहीं हो चुका है. बच्चों की रिक्वेस्ट की वजह से मैं रिक्वेस्ट करके मैनेजमेंट को इंस्ट्रूमेंटेशन का यूट्यूब क्लासेस ला के आया हूँ, क्योंकि मेजरमेंट्स एंड सीओए का क्लासेस है लिस्ट में, ECEE का इंस्ट्रूमेंटेशन का लिस्ट ही नहीं था. लेकिन बहुत सारा स्टूडेंट्स मुझे पिंग कर दिया, मैसेज कर दिया, सर हमको यूट्यूब क्लासेस चाहिए बोल के. लेकिन उस समय मैनेजमेंट एक्सेप्टेंस में नहीं था, लेकिन फिर भी हमने ऐड कर दिया. उसके बाद भी आप रिस्पॉन्स नहीं दे रहे. सो नेक्स्ट क्लास आई विल कैंसिल. दिस इज द फर्स्ट एंड लास्ट क्लास ऑफ ऑप्टिकल. So this is a responsivity. The responsivity is also called as sensitivity. What we call this as sensitivity. This is what we call as sensitivity. P optical by I bias, optical power generated internally by I bias current supplied, watt per ampere. Okay. So this is a responsivity. Responsivity into Q by EPH. So EPH means HC by lambda. HC by lambda. Chalo. Please answer this question. Make it fast. Answer. 6 into 10 power 6 EHPs are generated. So see here. So this is the LED. So from here 5.4 into 10 power 6 photons are generated. 6 into 10 power 6 EHPs are injected. So these are the photons. So internal quantum efficiency of LED is 5.4 into 10 power 6 divided by 6 into 10 power 6 into 100. So what I am going to get, 5.4 by 6 into 100, that is, if you take the percentage, it is 90% or else 0.9. But what is the next question? See here, is asking the optical power internally generated. So for that I can take internal quantum efficiency formula. So what is the internal quantum efficiency formula what I can take? 8 members are watching. Can you reply me? Anybody got the answer here? So that I can write as optical power divided by IPH. So internal quantum efficiency formula you can remember like this: rate of photons divided by rate of EHP. So rate of photons divided by optical power divided by energy of the photon. This is I bias by Q. So this is P optical divided by energy of the photon into Q by I bias. Okay, so this further can be written as P optical into Q divided by HC by lambda, that is I bias into lambda. Okay, so now internal quantum efficiency I can take it off. Optical power I need, so optical power I can take the formula like this: P optical is equal to internal quantum efficiency into H into C into I bias divided by Q into lambda. Okay, so internal quantum efficiency कितना है 0.9. So 6.625 into 10 power minus 34. So you please do calculation part. कितना आ रहा है calculation करके बताइए. So I can take off the calculation part and tell me how much you are going to get. Calculation part submit करके जल्दी बताइए कितना आ रहा है आंसर. Internal quantum efficiency का value कितना आ रहा है. You can use a calculator and tell me. So let us go for the next topic. Now in the optical sources, second part we'll do. So this what we have discussed, internal quantum efficiency. Now we'll go for the external quantum efficiency. So this is externally emitted power. the power which is externally coming is lesser than the internal optical power. Remember that always. The power whichever is coming external, that is the internal optical power, say comparatively less. So this is the optical power internally generated. So this is the optical power externally emitted, and this is the optical power coupled. Okay. So optical power generated internally and optical power coming out of the dome, that is external, and this is optical power coupled, P coupled. Okay. Chalo. Now if I see this optical power externally emitted will be how much? Optical power internally generated by 4 transmission factor into mu naught square by mu x square. Mu x square. Mu x is the refractive index of the semiconductor. Why? Because it is coming out of the semiconductor layer and entering into the air. Na? So optical power internally generated, transmission factor F into mu naught square by divided by 4 mu x square. So mu naught is the refractive index of the material. So what I am going to take here is, so this external efficiency. So externally emitted power, if you check, optical power internally generated by 4 F into mu naught square and mu x square. So this mu x square is our refractive index of the semiconductor layer. Okay, refractive index of the semiconductor layer. So definitely optical power जो भी external आ रहा है ना, वो comparatively optical power internally generated, that will be less. So P internal by 4 F into mu naught square. F is the transmission factor of the semiconductor interface. P into is the optical power generated internally. P external is optical power emitted outer. Okay, chalo. Next comes okay. So that is the context. So if you see now, external efficiency. External efficiency is defined as optical power externally emitted divided by optical power electrical input. So this is the optical power electrical input. So this is the optical power electrical input. So P externally emitted divided by P electrical input. Electrical power generated is given as V supply into I bias. External power emitted is P externally emitted, that is P internally generated divided by 4 F mu naught square by mu x square. Okay, so this is external efficiency. This is external efficiency. This is input electrical power. So externally emitted is externally emitted is this na. So what happens to the formula now? External efficiency formula, if you check, external efficiency formula, if you check, externally emitted, that is internally generated, F into mu naught square divided by 4 mu x square. Electrical power input, that is V into I, V supply into I. So this is what we call as external efficiency. This is what we call as external efficiency. Done? Chalo. Next comes the coupling efficiency. So next one is coupling efficiency. This is the coupling efficiency. So if you see the coupled efficiency for LED, so how much optical power externally emitted? to the how much optical power coupled inside. Okay, so that is what we call as coupled efficiency. Optical power externally emitted divided by optical power coupled. So coupled efficiency is given as optical power coupled to the optical power externally emitted, that is given as numerical aperture square. So numerical aperture square is a sine square theta a. Numerical aperture is given as what? Sine square theta a. So sine square theta a is the acceptance angle. So numerical aperture is that is a characteristic of optical fiber. So that is mu1 square minus mu2 square by mu naught. So mu1 is the refractive index of the core, mu2 is the refractive index of the cladding, so mu naught is the refractive index of the surrounding. Okay, so the acceptance angle is given by numerical aperture, that is sine theta a. So this is a sine theta a. Numerical aperture square is equal to sine square theta a. Okay, so make a note of it. Okay, so numerical aperture is a sine square theta a. So let us go for the questions. Answer this question. The radiative non-radiative lifetimes is given by, so TRR is equal to 60 nanoseconds. Next, TNRR is given as 100 nanoseconds. So from this we can take it as rate of RR, that is 1 by 60 nanoseconds, rate of NRR, that is 1 by 100 nanoseconds. Determine the total carrier recombination lifetime. So total rate I can take it as 1 by 60 nanoseconds plus 1 by 100 nanoseconds. Okay, determine the total carrier recombination lifetime. Okay, so that is 100 plus 60 by 60 into 100. So question here is total will be become as 60 into 100 divided by 100 plus 60. So this is 160, this is 6000. 600 by 16 kitna aa raha hai? 600 by 16, 6 members are watching, 37.5 nanoseconds will come. Next question, determine the total carrier recombination lifetime and power internally generated. So for that we can go for the internal quantum efficiency first. Internal quantum efficiency is nothing but the rate of total rate of radial recombination by total rate. So total rate कितना है? ये है total rate. Rate of rate we have 1/60. So I can write this as 1/60, and this is 1/60 plus 1/100. 1/60 plus 1/100. So 1/60, 100 plus 60, 60 into 100. So that is 1/60, 60 into 100 divided by 100 plus 60. Okay, so this will 60 cancel. So 100 by 160. That is the internal quantum efficiency. As a percentage, if you want to take, so you can multiply with 100. 100 by 160 into 100. 1000 by 16. 1000 by 16. So that is how much is coming. So that is a 62.5% is the internal. That means this LED emits a light of 62.5%. That means if you give 100 electrons to it, it generates 63 photons. If you give 100 electrons, it generates 63 photons. That means 37 it is not converted. 37 is a loss. Okay, that's a better efficiency. Second question, he asked some other story. Power internally generated, optical power internally generated. इसको कैसे कैलकुलेट करना? और एक फार्मूला भी है इंटरनल क्वांटम एफिशिएंसी का. इंटरनल क्वांटम एफिशिएंसी का फार्मूला क्या है? जो भी मैं बात कर रहा हूँ वो इंटरनल की बात कर रहा हूँ, एक्सटर्नल की बात नहीं है. एक्सटर्नल अलग रहता है, सब कुछ एक्सटर्नल अलग रहता है. इंटरनली सच है, समझ में रखो. ओरिजिनल है इंटरनल, एकदम बाहर आने के बाद क्या होगा? एक्सटर्नल एफिशिएंसी आएगा. एक्सटर्नल इज ऑलवेज फेक, इज ऑलवेज नॉट ट्रू. इंटरनल इज ओनली ट्रू. सो लेकिन रह नहीं सकते ना. जो पैदा हो गया इलेक्ट्रॉन, देखो ये डायग्राम देखो, ब्यूटीफुल फिलॉसफी है इधर. देखो इतना अच्छा ब्यूटीफुल डायग्राम्स कहाँ से मिलेगा आपको? सेल्फ मेड. दिस इज द जन्मस्थान ऑफ फोटोन, गर्भस्थल. सो यहां से फोटोन का जन्म हो गया, लेकिन ये यहां नहीं रह सकते ना, यहां से बाहर आना ही पड़ता है सोसाइटी में. वंस इट केम इनटू सोसाइटी, इट्स इंटरनल क्वालिटी गॉन. हियर इट वाज ब्यूटीफुल, here it was highly efficient, but once crossing the barriers of the layers of the society and came into the space, it has become external. The optical power externally emitted is always lesser than the internal. So whenever I will talk with the students, I will tell always be strong in internal. Obviously automatically external will be strong. अगर यहाँ आपको weakness है, यह भी आपको weakness हो जाएगा. Okay, so now the point here is I'm talking about optical power. ये पूछ रहे what is the answer? So this is the optical power divided by, here comes the IPH and here comes the EPH and here comes the Q. You have to remember like this. So this is the responsivity, this is the energy of the photon. So he is asking what is the optical power internally generated. Very good question, many times repeated question in the gate. अगर आप मेरा YouTube series ध्यान से पढ़े तो I will assure you minimum to minimum 60 marks are guaranteed in the gate examination for instrumentation students. All over India, rank 1 came for the instrumentation student last year. AR1, Mr. 𝐂𝐤𝐴 is from our branch, instrumentation. So this is the formula. Okay, so ये 62.5% है ना. So that means 62.5 divided by 100 करो तो कितना आएगा भैया? 0.625 आएगा. Energy of the photon का formula क्या है? Energy of the photon physics, hc by lambda. h कितना substitute करना? 6.625 into 10⁻⁻34. c क्या है? Velocity of light. That is 3 into 10⁸ meter per second. And photonic current कितना है? क्वेश्चन में दिया भैया. photonic current देखो एक बार, 40 milliamperes. So the driving current is 40 milliamperes. So this is the driving current 40 milliamperes. तो सब्स्टिट्यूट करो, कैलकुलेशन अच्छी तरफ से करो. गेट में राउंड ऑफ नहीं करना. अगर आपको 0.625 आ गया, डोंट राउंड ऑफ टू 0.63. अगर आप वैल्यू को राउंड ऑफ कर दिया, आपका रैंक भी राउंड ऑफ हो जाएगा. सो प्लीज रिमेंबर आफ्टर डेसिमल प्लीज टेक 4 डिजिट्स. Okay, so Q is 1.6 into 10⁻⁹ coulombs. One thing is missing here. Energy of the photon is hc by lambda. What is a lambda? That is a wavelength. So wavelength is given. So lambda is a wavelength that is 0.87 micrometer. So this is a 0.87 micrometer. So this is 0.87 into 10⁻⁶. So please simplify and you are going to get द आंसर नाउ। सो इंटरनल क्वांटम एफिशिएंसी, सॉरी ऑप्टिकल पावर का आंसर आ जाएगा आपको, ऑप्टिकल पावर का आंसर आ जाएगा। ओके, सो कितना आएगा 0.625, 6.625 इंटू 10 पावर माइनस 34 इंटू 3 इंटू 10 पावर 8 इंटू 40 इंटू divided by into divided by into. Okay, please calculate how much you are going to get. I think around 3.5 microwatt something here. Please calculate this part. Okay, chalo, maza hi maza. Last question for this class, so try to answer this question. Answer this question. अभी रेस्पॉन्ड कर रहे हैं अभी गार्डियन, अब तक कहाँ गए भैया? या सो प्लीज सॉल्व दिस। कितना आ गया? The light output from a gallium arsenic LED is coupled in optical with numerical aperture. So numerical aperture is, so coupling efficiency is nothing but numerical aperture square. So numerical aperture is given as 0.2, so 0.2 square, so that will become as 0.04. Percentage, it will be 4%. Next, the optical loss in decibel related to power emitted. So optical loss means 10 log base 10 by optical loss in decibel related to power emitted from LED. So optical power coupled divided by optical power externally emitted. So this is nothing but efficiency, that is 10 log base 10, 0.04. So what we can write, log of base 10. Yes, yes, excellent. कहाँ से हो आप? Log 0.04 into 10, so minus 14, minus 13.97 decibel. So these are the topics for today. So I am giving this question as assignment. So please answer this question for tomorrow. Okay. So enough for today. So आज का क्लास में मैंने ऑप्टिकल फाइबर, ऑप्टिकल एलईडी का पूरा कंटेक्स्ट डिस्कस किया था. So ये कंटेक्स्ट आपको मैं फॉरवर्ड कर रहा हूँ. ये अनटैप्ड कंटेंट है ये कंटेंट. ओके, सो इसके यूज करके आप अच्छी तरफ से प्रैक्टिस कर लो. ओके, सो नेक्स्ट क्लास हमने स्टार्ट करेंगे ऑप्टिकल डिटेक्टर से. नेक्स्ट क्लास हमने स्टार्ट करेंगे ऑप्टिकल डिटेक्टर स्टार्ट करेंगे. सो मिस मत करना क्लास को. ओके ना, थोड़ा समय पर आ जाओ, अच्छी तरफ से कंटेंट डिस्कस करेंगे. इज ऑल फाइन? चलो, थैंक यू.